טוב, ערב טוב לכולם, ברוכים הבאים לעוד סשן מספר 4 של האקדמיה. אקדמיה זה פרויקט של חברת פארגון קבוצת ברנע של שיתוף מידע מפי מומחים מהארץ ובעולם. השבוע הצטרף אלינו מר מקס לקונן, מקס מנכ"ל מעבדת בדיקה בשם IFAB, המעבדה החברה תחת מטריית איגוד המעבדות האירופאי ILAC. מקס עצמו גר בפינלנד, אגב פרט מעניין, בשיחה שדיברתי איתו, הוא מחודש מרץ ועוד לא היה במשרד שלו בברלין. אבל מקס יספר לנו על נושא של פרויקט מאוד מעניין, פרויקט סוברן, זה פרויקט של מימון ממשלות אירופאיות, לבחינת הכיבוי של דלקים אלטרנטיביים ושל רכבים חשמליים ואוטונומיים. מקס, please, the crowd is yours.
Thank you, Omri. So, as Omri most likely already gave an introduction, so today we are going to talk about the new energy carriers and autonomous vehicles, and basically under the topic of new fire safety challenges. The presentation today is going to have these elements. So first I'm going to introduce myself a little bit more in detail, a few words about the company IFAB, and then I'm going to focus to the fire engineering in future. And today we are talking about the transportation. Then this is a kind of appetizer then for the research part, which includes the Sovereign Research Project, and finally I will summarize to some of the conclusions. So my name is Max Lakkonen, as you probably heard. So I'm from Finland, working in Germany, but obviously during these times it's been a bit difficult, this combination. And I mainly have been doing some remote work. I'm having very much of technical engineering background, different fields, but in fire safety engineering, I've been working now for over 15 years, starting with the manufacturing side, and nowadays quite many years just in the design and consultancy. What is probably worth of mentioning is obviously these different assignments for committees like NFPA 130, 502, 750, where I'm the principal member of the technical committees. I'm also working very much in the underground world and the member of board in the ITA Kosovo. Some other things, so I've been in academics. I know that there are also university folks listening and watching, so I've been also in academics over 10 years. And I have quite some papers and some patents. But most importantly, what I am, this is more the professional. On private side, I'm living in a country where we have a lot of opportunities to be in the nature, and that's where I'm also spending my free time. So pretty much hunting, fishing, dog training, and yeah, that's about me. Then a few words about the company IFAB. IFAB stands for the Institute of Applied Fire Safety Research. We are the design and consultant office, but we are also an accredited fire test laboratory, and this combination is quite unique. So we have the experimental side, and then we are having also the more, let's say, the engineering side. Our headquarters, they are based in Berlin. We do have also a fire test hall in different part of Germany. We are actually very, very international. So a big part of our work is actually outside Germany, and we are specialized to kind of special hazards, a lot in transportation, but mainly for when there's a topic of something new or something different. Application areas, so buildings, industrial, that's more the bulk, but then rail, tunnel, metro, that's where we are very active, and nowadays also working with the lithium-ion batteries. And this is now the topic also for today to some extent. Here, just to show some of the brands we are continuously working or we've been working with. So this gives you a bit of the spectrum of our clients. But then moving to the topic for today, so we could put it under umbrella of fire risks in the future of transportation. And before diving in further, important is to define the risk and fire risk. I mean, from the risk engineering. So risk is always the probability multiplied by the consequence. And today, if we are putting to the risk engineering map, so I want to introduce this autonomous driving, and this has mainly to do about the fire probabilities, what's going to happen, and then what are the scenarios which are likely to happen in future. And when talking about the consequences is then when we are talking about what kind of vehicles will be burning and whether the consequences are different that they would be with the conventional vehicles, for example. Today, the focus is very much on the latter part, so talking about the new energy carriers. But nevertheless, I think it's important to understand that the cars, they actually are already utilizing autonomous driving, and then this is a very important thing. I mean, when we are looking how the technology, I mean, all kinds of technology, not just fire engineering, but how the technology has been developing, let's say, within the last century. So it's been very exponential. If you look to the right side pictures, so the one on very bottom represents the way of transportation of my father from the hospital to home when he was born. So that was very conventional, but very sustainable at the same time. The picture in the middle, this old Volvo, that was actually the car which took me home from the hospital when I was born. And the picture on the upper corner is actually not the car which was used to my oldest daughter to be transported from hospital to home, but that just shows that already that time there were vehicles without drivers in traffic. So already within these 3 generations, the transportation has changed a lot. Many people, they consider that this whole topic would be science fiction, but I mean, that was probably a bit of my topic, my skeptic view in past, but especially seeing this kind of videos. So this is actually 10 years ago, showing that a kind of media event when the automatic braking system was introduced to public. And as you see, this demonstration did not go too well. But now 10 years later, the very same technology is in practice, it's utilized, and it saves lives. So yes, autonomous driving will come. I don't go through the specification that how it's going to how it's been defined, but this is a clearly an effect which is going to or this is the thing which is going to have an effect to our work in future. We already now are considering that how should we operate, how should we do the infrastructure, how should we build, let's say, communication to the fire and rescue services. But but the fact is that this part of the technology is developing way too fast. And we see, for example, in our NFPA work, that we can't follow the technology as it develops so extremely fast. And the key question is how this is going to influence the accidents leading to fires in the future, or how is it going to operate with the fire and rescue services? I mean, whether the cars will recognize the firemen on the road or the rescue vehicles, and infrastructure will communicate with the cars. So yes, to summarize, let's say the first part, autonomous driving will come, and that's going to have an influence to, some say positive or negative, how accidents and accident leading to fires will happen. But today we are not going to focus much more to that, but we are more looking at how the future cars would look like, and there we are jumping from the fire probabilities to fire consequences, and then we will immediately enter to new energy carriers, a kind of new way to provide the energy, the fuel for the cars. And at the moment there's a lot of different things which would be ranked as a new energy carrier, and I have to say that I think electric ones are the ones which we are obviously seeing much more in media and by various reasons, because they are often related to the passenger cars. But this is definitely something which is also linked for the autonomous driving, because often 98% of the automated cars, they are also utilizing the electricity. And NFPA calls this as alternative fuels, by the way, as a side note. But I would do as we have had these interactive parts in this webinar, so I would actually ask from you as the being the voting members, that what do you think that what's going to be the most used fuel technology of passenger cars in 10 years? And I suppose that the vote is on. I don't know. Okay, I don't see any results yet.
Lilach will share it.
Okay, thank you. All right, so I see that we got, let's say, the similar results, that we had 43% as a mixed use, and 43% for the electricity. Gasoline, 14%. I actually can't say which one it would be, but I just have to count on the estimates what the more clever people are giving. And yes, for sure, the electric driven vehicles are considered definitely now the probably the most attractive. And there's a lot of question that whether they are sustainable, how environmental friendly they in the end will be, but we see that there's a lot of political pressure, giving the pressure towards one or the other technology. But the fact is that, these technologies, they will increase very quickly, but there are no harmonized laws between countries or the continents. But the key question is that what this has to do us as fire engineers. And obviously new energy carriers and fires, they have got a lot of media attraction. So this is what you probably have seen in you know, in media when there's a or buses exploding, so that always reaches the media, and especially the electric vehicles. They have had a quite bad track record in terms of fire incidents, but which is a kind of normal when the technology is evolving. It's for sure that the new energy carriers, they will provide some special challenges for the infrastructure, for fire services, and the fire characteristics. And there has been now a lot of discussion about the electric vehicles, whether it's a fully electric or hybrid one, but how safe they are or how risky they are from a fire point of view. And then I would also ask another poll that how about you? I mean, do you consider electric vehicles, EVs, more or less dangerous than only with conventional combustion engine? If you consider them more dangerous, then you could vote yes. If they consider them less dangerous, then you could vote for no. We are weighing the voting results, but this is a very key question. We are working very much nowadays with the electric vehicles, and I see that we got the results 50-50. So I think that represents probably also the scientific world answering. Actually, there are certain elements. So electric, whether they are fully or partially, they are not really considered producing much higher heat release rate than conventional cars, so the cars having the internal combustion engine. So probably for the heat release rate, I don't see that there would be a major difference. There's one thing which is a problem. I could tell you the history where it's coming from, but in general, the heat release rate from the cars and the energy content has been kind of probably calculated a little bit too less when comparing to the design of the modern cars, how much combustible material they are nowadays having, and they are much larger than they used to be. So I think in that sense, it's probably not so drastic, but where there is definitely a difference is the combustion products. So, and now I'm referring to lithium-ion batteries. So yes, they definitely they have more aggressive, toxic gases being produced, and this can cause some precautions, for example, for the rescue personnel. This can be a problem with, let's say, all enclosed facilities, and often I'm looking often from the underground world perspective, so that they are always confined. But where there's also a major difference is the extinguishing, and we have seen it that they can be a problem for the fire services, also for the equipment being carried, and obviously the reignition, and there are certain elements which do not exist with the internal combustion engine cars. we have to look also in a little bit in a broader view, that the batteries just in the car, that's one risk. But now when the cars will change to the cars will change to use lithium-ion batteries in large quantities, so that we will see these batteries being transported on the streets, in the tunnels, and obviously we are now having one hazard also in kind of different parts of infrastructure that in many countries, which is quite funny, by the way, I have to say, that often when you are transporting the lithium-ion battery on a truck, it's considered as a dangerous goods. But when it's inside the car, so then it's probably not, then it's not considered as a dangerous good. But nevertheless, I think this is one aspect to be considered. But typically tunnels, they are built anyways for dangerous goods, so they should be safe. But we see the same kind of challenges on other part of the infrastructure. So when the batteries are stored at car dealers, service garages, so we need to make sure that we have the right precautions made also from the fire engineering point of view. And that's going to be a change. I don't think so that would be a thing that we would need to be afraid, but we just need to address that in the design. So in that sense, changing of the vehicles will influence the infrastructure as well. When talking about the different gases, fuels, they will obviously have a totally different combustion characteristics. So and we are having elements like explosion risk, gas clouds. I mean, how to ignite the gas clouds, or if we are having leakages, whether ignition is possible. Also, in terms of the first responders operation, and obviously this very fast energy release. We're talking about time, temperature, and the impact area when we are having hydrogen involved. So obviously the flame temperature can be very high. But again, new elements which we did not have in past. And all of these topics, which I was just looking now from different angles. So luckily there is also research ongoing. And one of the research programs which been ongoing in recent years has been called Zaren. And this Zaren is actually it's funded by the German Ministry of Education and Research. It has a various, let's say, main members and then associated partners, different organizations. Our role as a IFAB was to carry out the experimental tests. Zaren stands for the safety of urban underground structures when using new energy carriers. So again, combining new energy carriers in confined space. So we want to collect and isolate all risks to enclosed space, and obviously that's kind of worst case scenario. The project itself, I mean, you can have a look for this webpage. That will tell you also a bit more about the research project, but the project consists of different working packages. As often it started with the literature studies to understand the problemacy and what's been done by the others. Then it focused on the defining different risk scenarios, which would be kind of the most interesting ones to study, and would be representing typical cases under this topic, and then further moving these risk scenarios to real case studies, looking what it would mean in this part of the infrastructure or that part of the infrastructure, with the real dimensions, real dimension and real challenges. And then further, it included the numerical simulations and experimental tests and testing of different mitigation measures. And finally, it's in the last stage where, let's say, the impact on safety is now reported, and a kind of best practice is going to be put into the guidelines and being brought then public. When talking about the new fire risks, I already discussed about two main topics. So one is more, let's say, pressurized gas. So different gas storages being utilized, and another, let's say, mainstream, which I would say currently is much larger, is batteries. I mean, lithium-ion batteries, and they obviously have different characteristics when we are having fire risks, and our work was primarily involved to the batteries, and obviously there are different risks involved. So it's the fire sites, how to extinguish the fire, what are the combustion products, the different toxic gases, and then obviously the risks with what they can cause in addition, so high voltage or reignition. And when dealing with different gases, so obviously then we are talking about jet flames, pool fires, I mean, total different characteristics, which we also see here with these two videos. One on the left hand side is in the Hakebach test gallery, the test with the batteries, and then on the right hand side you saw the CNG bus from Stockholm. So that also demonstrates a bit that how giving an idea about how different kinds of fires we are dealing with. I mean, due to the limited time, I would now focus a bit more for the outcome so far of the Sovereign project. So I'm going to discuss first, let's say, the engineering part, and then I will focus on the experimental side. But I think one of the key elements which been let's say developed within Sovereign project and these studies is the design tools. And I think we can have prescriptive approach. So I mean, looking everything black and white, providing the minimum requirements, what shall be done. And this is obviously very much of the NFPA approach. Or we can go for the performance-based design in under, let's say, NFPA terms, more engineering analysis, I think is the correct word. But I think this is now noticed to be the best way to tackle these special hazards, special risks, and especially with the evolving technologies. So looking what would be the best solution, best mitigation strategies, depending on the risks which we are having. So performance-based design obviously is very known with the special hazard design in fire risk engineering, but utilizing this also with the infrastructure which are having NECs involved. And one of the things, obviously, for the standardization is, for the prescriptive tools, is that the technology is just evolving so quickly, not just in terms that what kind of energies they will utilize, but as we discussed also earlier, that they might be also tribalized, so they are going to influence also to the typical incidents which we are potentially having. CFD has been in a major role in Sovereign, and there has been developed also a kind of design tools which would help to study, to model the conditions, for example, in underground car parks or in any enclosed car parks, in terms of car-to-car fire development, or what kind of conditions there potentially would be for fire services. And obviously, since there have been also the empirical tests, so fire tests, so trying to utilize this data to CFD, having a kind of semi-empirical models. And why, for example, these car parks, closed car parks are of the topic, is that there happens quite frequently some major fires. There was on the 19th of November, there was in Berlin, very large fire. I think there was some like 30 cars involved. Obviously, this is a very small compared what happened in Liverpool. I think it's 2 years ago, where there was 1,400 cars involved. But nevertheless, this just addresses that there is a need for the research, like Sovereign, to study how to prevent fires spreading from one vehicle to the other. What is also very interesting is that the kind of design guidance, especially related to the performance-based design within the Sovereign project, is the new design fire curve. And this covers, let's say, all passenger cars, so including new energy carriers, internal combustion engine cars, and it also takes account the size of the typical modern car, as well as the material composition. So this is very important for the designers, that how to design, what kind of burning characteristics I'm expecting. And here's the curve. It's based the number of fire tests with the different kinds of vehicles, with the different energy or different fuel systems. So there are EVs, fully electric vehicles. There are hybrids. There are then the cars with the normal combustion engine, and this is also something which was important for the designers. Then moving more for the experimental testing. So there were a number of fire tests also within the Sovereign project, and there were fire tests where only the batteries were tested. Here, this is the video which shows you the well, I would say quite typical burning of the lithium-ion battery. This is in size of 30 kilowatt hours, so probably more on the hybrid side. And here we see very clearly that when it goes from cell to cell and then from model to model, the fire development. What was also interesting was that the heat release rate was measured in different ways. So there was a kind of new development how to do the heat release rate measurement. Was always difficult with the batteries, as we are having, let's say, chemically stored energy as well. then what else was within the Sovereign was that there was a lot of data measured with the FDIR. So so a lot of gas analyzing, and because there's a lot of discussion often with the certain elements of the combustion product and their toxicity, and which was also noticed that the reignition happened, especially with the tests where different extinguishing methods were also tested. I think it would take too much time to go through all the results, and they will be published within the research project. But I just wanted to demonstrate a typical burning characteristic of the battery itself. And here on the upper picture, you see the typical fire of the battery, where it goes from kind of model to model. So the fire slows down a little bit, and then the next model will kick off, and then it burns in a kind of segments or compartment. And obviously, if this has to do also with the battery casing, so more fire retardant battery casing, for example, we are having between the different models, so we can have a totally different fire curve or the heat release rate measurement than with the one which is, for example, having just with plastics. Obviously, HF, hydrogen fluoride, that's been discussed very much from the perspective of health and safety of the fire services, and we also did measure relatively or decent amount of it, probably not that high than some of the previous research suggested, but there's going to come also a separate paper about this topic. There was also some other fire tests, and one interesting thing was to do a kind of generic mock-up for simulating a car, so car of any type. That's been always a little bit of the challenge, that when doing fire tests with the one type of the car, I mean, we take one model and we do the fire test, but then we take a different model, so that's going to burn in a different way. That's why we normally, when we are doing standardized fire tests for different risks, we are having a protocol which which will define the fire load. And within the Sovereign, it was also developed a kind of generic car design, including also the battery, and that was also very unique, very interesting, and that's the way that different, for example, different technologies can be tested with the similar conditions. And as part of the fire test was actually also testing different fighting and detection technology. You see that there were quite different number of suppression systems, for example, being tested. Here's some footage from the fire test with this car mock-up. So very simplified, but having the battery, having their wood, and then obviously protecting it, challenging the different systems, and then doing kind of comparison tests with the different technologies. So this gives you a bit of the idea of what also IFAB is doing on a, I would say, on a weekly basis. We run some sort of fire tests. The last but not the least is the guidelines. So Sovereign Research Project is going to publish a kind of final reporting in form of guideline. The intention is to give the knowledge which been gathered and collected to provide this to the designers, and that's been also the interest of the ministry to distribute this knowledge which been done in the research project. The good news is also that this is going to be published, as far as I know, in English. Also, the web page is bilingual. So that's about the Sovereign project. And now to conclude or to do some conclusions based what I just presented. For sure, many parts or many different engineering fields are going to change in future, and that's going to influence also fire safety engineering. And now when we are talking about the context of the transportation, so we are going to see much more autonomous vehicles. This has to do with the fire probabilities. This has many operational sides being involved. And secondly, the cars, they are not just changing from the driving mode, but they are very, very quickly changing what kind of energy source they are having on board. And that's when we are talking about new energy carriers, and there we are talking more about the fire consequences. So what kind of fires we will have with such vehicles. NECs, they develop extremely fast. They have major impact due to the new challenge set for the confined spaces. So yes, they are, I mean, like underground, when having the inside the box any kind of fire, then we are obviously challenging the operations, the systems, and especially lithium-ion batteries are considered risky, I would say. I think there's a lot of, let's say, gut-based feeling, but we also see that the lithium-ion batteries, they have a certain challenging elements, like the combustion products, which are more aggressive, toxic. Firefighting, extinguishing is very difficult, and then impact is not only for transportation. I mean, with the lithium-ion batteries, the impact is it's not only for the vehicles, but also for the surrounding infrastructure. And we also have to remember that there are also some other new energy sources, and one is different gases, and there we are having total different risks. So I mean, with the hydrogen, as I said, flame temperature, the impact of the jet fire, or potential explosion risk. Sovereign Research Project, to summarize it, so that's tackling exactly with the issues with the NECs. It's going to include some best practice tools for the designers as the final reporting, and it's supporting the performance-based design. Sovereign had very interesting fire tests with the lithium-ion batteries. I would say very unique data with the gas analyzers, and then secondly also these comparison tests of different firefighting or fire suppression technologies or fire extinguishing technologies. CFD development using the semi-empirical models, again something new, and last but not the least is the fire curve for modern cars. And that's for you a kind of short introduction diving into this world of the fire engineering. And we don't know what the future will bring. I will finish my presentation for another way of the future, which is the Hyperloop project, where I was doing the fire engineering for the prototype track when they were applying the building permits. So thank you very much for your interest and time, and have a fire safe travels.
Yeah, thank you, Max, again. Everybody can ask question at Q&A. You have below the button. Max, we have some questions, if I will ask you. How the energy involved in a fire related to the amount of electrical energy stored in a battery? What is the minimum charge level that does not cause a fire? Did you have any experience with it in a Sovereign project?
Yeah, I would answer. I mean, there are two different questions. So for sure, I mean, when talking about the car, so the car, it includes of the battery and the car itself, if that was the question. So in the car, the battery is only one element. Okay, if we are, and then there I would say that if it's a full EV, so fully electrically working, then obviously the car plays a major role. So, and then the charging stage of the battery has also an influence. But if we are talking about the battery itself, and then when we are talking about the level of charging, so then it's way bigger. It's much more important. So then it really plays a role whether it's 30% or 100%. And the last question, that what is the minimum charge level that does not cause a fire? I'm not really sure if there exists such thing. Obviously, we are having some sort of level there, and this, for example, with the mechanical failure, can lead to yeah, I'm just thinking whether this could be, and the other trouble which we are having in real life is that often the batteries, they will not go to 0%. So I think that if we would consider as a mitigation method that we would keep the batteries, just in 0%, that we would not have the fire risk. I don't think so that this would be possible in real.
Mm-hmm. Okay, we have another question. What was the final conclusion of this project? Which system is the most effective? I know it's a very wide question, but try to limit it.
Yeah. I think this refers more to the different firefighting systems. I think there it's a difficult to say which would be the best one. I'm not sure what I'm able to say in this stage, but I think it's I would say that water-based systems in general, they were good, and there are some important factors, because obviously if it's also then that how much water you will apply. So I mean, there are different variables which you are having, the droplet sizes, so obviously the mist systems, they are having, in terms of cooling, they are having certain benefits, and which make them also efficient, and which might be that in some other applications like you know, in enclosed spaces, that will work very well. But then when it's a bigger storage or something, it might be more challenging. But I think in general, I would say that water-based, they are good. But I'm sure that there's going to be also some publications about these topics. And then we also noticed that there were quite interesting measurements, for example, with the combustion product being noticed depending which agent was used. And I think that's something, this part of the work probably has not been done in any other context.
Okay, we will wait. We'll be patient and wait for the results, official results, because I can see that you are speaking very, let's say, politically, and not want to do something that is not allowed yet. So it's okay.
Yeah, and these tests also the last tests which were done was just a few weeks ago, so it's very new.
Okay. Another question, we will finish with this one because we get more and more questions, but is there any hydrogen released during charging of lithium ion, and is it been measured?
This is a very good question. We did not we did not do this measurement. I know that this has been in the research field, that has been a topic, but in this context, we did not consider this being in. I mean, we were more looking to the vehicles, and that would have been the major topic of this research work. I mean, potentially there is such topic, but I would consider that being a minor thing from our perspective, how we looked these vehicle related applications.
Okay, thanks again for your time, and have a good evening in Finland.
Thank you very much.
Thank you all. תודה רבה לכולם. אנחנו בהרצאה בעוד שבועיים, ההרצאה הבאה של נדב אברג'ל, מהנדס חברת פרגון קבוצת ברנע. אנחנו נעשה הרצאת היכרות על מערכות ערפל מים, נסביר יתרונות טכנולוגיים, סוגי מערכות, מבחני אש ודוגמאות מפרויקטים הארץ והעולם. אז תודה לכולם. Thank you again, Max, and bye to everybody.
Bye.